After this fairly lengthy review, let's now start the second part talking about writing and balancing chemical equations. When you write and balance a chemical equation, you usually start out with a word equation, something that tells you what happens. Methane combines with oxygen to produce carbon dioxide, water, and heat. Or hydrochloric acid combines with sodium hydroxide to produce sodium chloride and water. And in order to write an equation for that, which is a shorthand to help us understand what's happening, you first have to write the chemical formula for each of the chemical compounds that is in the word equation. And then after you write that down, you have to subsequently balance the formula with coefficients in order to preserve the law of the conservation of mass. So here's the first one here. Here's potassium chloride plus magnesium sulfide combines together to produce potassium sulfide plus magnesium chloride. So let's look at how we would write this down. First of all, we would write down the formula for each of these names. Potassium chloride was KCl, and it combines together with magnesium sulfide, MgS. Now, if you need to, on a separate sheet of paper, I'm not going to do this because it'll take too much time, but if you need to go through the least common multiple thing, you can do that to see how mine is correct here. And this combines together, that's usually an arrow, to produce potassium sulfide, K2S, plus magnesium chloride, MgCl2. Now, you'll notice right away you have two potassiums and two chlorines here. And you only have one potassium, one chlorine here. So this coefficient is to add a number outside here that will balance these atoms. Now, you never change this formula in order to balance it. You always use coefficients to balance. So this is a balanced equation which represents this word equation. And if you type this out versus writing all of that out, you see that this is much simpler in terms of being easier to do. So let's look at some more of these examples. Write a balanced equation for each of the following. So potassium sulfite, now we know that the sulfite is the SO3 and it has a -2, so it's going to be K2SO3 plus barium bromide, which is Ba, and it's a +2. Bromine is a -1, so it's going to be subscript 2. These combine to produce barium sulfite. Barium's +2 and sulfite is -2, so it's just like that. You don't really need those parentheses, but I put them in there. And then plus potassium bromide. And what you see here is you have two here and two here, but only one here, so you need a coefficient of 2 here to balance this equation. And what these two equations tell you is that one molecule of potassium sulfite combines with one molecule of barium bromide to produce one molecule of barium sulfite and two molecules of potassium bromide. So the ratio is 1:1 to 1:2. Let's look at this next one. Sulfuric acid plus copper. So H2SO4 is sulfuric acid plus copper, which is just a metal, reacts together to produce copper sulfate. And I didn't put 1 or 2 here, so that was my mistake. I should have put copper 2 sulfate to tell you that this is the formula for it here, plus hydrogen gas. And remember that there's some polyatomic atoms. That is, they only exist in pairs. And the polyatomic atoms are hydrogen, oxygen, fluorine, chlorine, bromine, and iodine. And whenever you write these in equations, they always have to be two of them together like this. And you just have to memorize that these are the polyatomic atoms. So we look here, we have two here and two here. So it's balanced the way it is. So one atom or molecule of this combines with one atom of that to form one molecule of this and one molecule of that. Electricity is applied to water to produce hydrogen and oxygen. So water, and you can, use a little delta or whatever to imply electricity. And then remember, hydrogen is one of these polyatomic guys, or diatomic guys, so it's like this, and oxygen is like that. And so you have two of these and two of these. That's okay, but you only have one here and two here, so you need to put a 2 here. But now you have 4, so you need to put a 2 here. So 2 molecules of water produce 2 molecules of hydrogen and 1 molecule of oxygen. The last one here, carbon dioxide and water combine together to produce glucose, and I gave you the formula for that, and oxygen. So carbon dioxide and water combine together to form glucose and water. You might remember this reaction, oxygen, from biology class last year. This is the process of photosynthesis. There's light energy here, and you have 6 carbons here and only 1 here, so we put a 6 here, and you have 12 hydrogens here, and you have 2 here, so you need a 6 here. And now you add this up and you have 12 oxygens here and 6 here, and you only have 6 here, so you need to put a 6 here to get the other 12 that you need to balance this equation. So 6 molecules of carbon dioxide and 6 molecules of water form 1 molecule of glucose and 6 molecules of oxygen. Now let's move on and look at the different types of reactions. There are 4 common types of reactions that we talk about. There are more than 4 types, but there are 4 types that I will introduce you to. The first is the composition reaction. A composition reaction is a reaction that combines 2 or more substances together to form a more complex substance. So for example, zinc plus oxygen forms zinc oxide. In the previous practice, that last equation where we were forming glucose, that's a composition reaction as well. A decomposition reaction is, as its name implies, is exactly the opposite. It's where you break down a complex substance to form 2 simpler substances, 2 or more simpler substances. So here we have potassium perchlorate. It reacts with heat and forms potassium chloride and oxygen. So this is a decomposition reaction. The third type of reaction is the single replacement reaction, and this occurs when an element in a compound is replaced by another element, but there's only one replacement. So in this case, zinc replaces barium and goes from barium sulfide to zinc sulfide. So this is a single replacement reaction. A double replacement reaction is where the 2 compounds swap anions and cations. So here we have potassium chloride and lithium nitrate swapping places so that you now have potassium nitrate and lithium chloride. So for each of these, let's see if you can identify the type of reaction that each of these reactions is. And if you need to, you should stop the tape so that you can formulate your answer, either write it down on paper or in your head, and then turn the tape back on and I will tell you the answer. So here's the first one. You have calcium chloride plus magnesium goes to form magnesium chloride plus calcium. This is a single replacement reaction. The magnesium is replacing the calcium, and it takes the place of the calcium with the chlorine. This is what we just looked at. This is the electrolysis of water, and this is a decomposition reaction. Water is more complex than hydrogen and oxygen, so this is a decomposition of water into its elements, hydrogen and oxygen. Here we have barium sulfate plus zinc oxide goes to form zinc sulfate plus barium oxide. And this is a double replacement reaction where the two anions and the two cations switch partners, sort of like a square dance where you swing your partner around and then you switch to the next partner. And here we have iron plus oxygen combined together to form iron 3 oxide. This is a composition reaction. You start with two simpler compounds, or two simpler elements in this case, and form a more complex compound. Now, another type of reaction is something known as an oxidation-reduction reaction. An oxidation-reduction reaction occurs when there's a change in the oxidation state of one or more of the reactants. There's almost always, or there is always, an oxidation and a reduction. When oxidation recurs, the reactant loses electrons during the reaction. Think LEO, L-E-O, stands for loses electrons, is oxidized. Reduction occurs when the reactant gains electrons. Think GR, G-R-R. And the mnemonic is Leo says GR. GRR stands for gains electron, as GER, excuse me, gains electrons reduction. Now, when you write oxidation reduction reactions, the most common way to write these is to write them as two half reaction. One of them represents the oxidation side, and one half reaction represents the reduction side. The reducing agent is the agent that is oxidized, and the oxidation agent is the agent or substance that is reduced. And we already talked about the oxidation number, and we've practiced how to do oxidation numbers. So, in any particular process, you start with a compound that, if you first look at the A side. The A side loses 2 electrons. Okay, so A, Leo, is oxidized. It is the reducing agent. So it is oxidized to a oxidized form. On the B side, you have an agent that gains 2 electrons. It gains, so it is reduced, and it is the oxidizing agent. And here are the two half reactions. You can see that zinc loses 2 electrons to form zinc 2+ ion. That's a process of oxidation, and zinc is the reducing agent. Hydrogen gains 2 electrons. 2 hydrogen ions gain 2 electrons to form hydrogen gas, and it is reduced. It is the oxidizing agent. Here's another example. Iron loses 2 electrons to form iron 2+, so it's oxidized, and that side is called the oxidation side. Copper gains 2 electrons and becomes copper solid, so it's the reduction side. It is reduced. Copper is the oxidizing agent. Iron is the reducing agent. So let's finish up this part by doing a few possibilities. For each of these reactions, you write the half reactions, then you tell which is oxidized, which is reduced, which is the oxidizing agent, and which is the reducing agent. So here's the first example. So let's go on and do this on a piece of paper. Actually, here's all 4 of them, so you can get right to the point. So here, let's do the first one here. First of all, you have zinc, and zinc is a metal, and you have 2 of them. and it's going to go to form 2 zinc 2+ ions. Now in order to do that, it has to lose 2 electrons, and there's 2 of them, so it has to lose 4 electrons. So that's the half reaction there. Since it's losing, this is the oxidation, or the element that's oxidized, and it's the reducing agent. And so the other half reaction is oxygen goes to form O minus 2 and there's 2 of those because of this 2 right here. And in order to do that, it has to lose 2 electrons for each atom, so a total of 4. And notice that this and this are balanced together. This is the reduction side. The oxygen is reduced, and it is the oxidizing agent. The next one is zinc again, and it again goes to zinc plus 2. And there's just 1 of them this time, so you only lose 2 electrons, and it again is the oxidizing side. It's the reducing agent. And in this case, the barium goes from Ba 2+ to Ba by gaining 2 electrons, and it's reduced, and it's the oxidizing agent. The third one here, we have iron. We have 4 of them, and these 4 irons are going to form 4 irons that have a 3+ oxidation number. So a total of 12 electrons, 4 times 3, has to be lost. This is the oxidation side, and this is the reducing agent. And then this one, the other one is oxygen again. There's 3 of these, and it goes to form 2 6 altogether. 3 times 2, 6 oxygen 2 minuses, and it has to gain 12 electrons in order for that to happen. So it's the reduction side. It is reduced, and it is the oxidizing agent. Now this one's a little more complicated. So if you look at this, you see that this I here changes to a different kind of I. This is a -1 here. This is a -1 here. But here, it's +1, -6, so it's +5 here. So you go from I +5 to I -1. In order to do that, you have to gain 6 electrons. At the same time, you see this is +2, but this one's +4. So this goes from Sn +2 to Sn +4. And in order to do that, it has to lose 2 electrons. And so this is the oxidizing side, the reducing agent. And this is the reducing side, the oxidizing agent. And you can see right away you're going to have this whole side multiplied by 3 to balance these electrons out. And we're not going to do that in this class, but this is part of the way that you balance more complex oxidation and reduction reactions.